Hello, good morning, everyone. We're waiting for more students to join and we'll start.
Hello.
Okay, good morning once again. Welcome into our yet another, I believe, 13th lecture on analytical geometry and linear algebra. Today we're continuing with a very exciting topic we started last time, which is, if you remember, the two-body problem and the Keplerian orbital motion. So, last time we have considered the motion of two gravitating bodies with masses m1 and m2 in the inertial space. There are no other physical forces acting upon them apart from the Newtonian gravitational attraction between the two bodies. So we first derived the equations of motion for m1 and m2 in the inertial space, and then we considered a relative motion of, let's say, m2 with respect to m1. We introduced the radius vector of m2 centered on m1, which we denoted by r. If we now connect our coordinate system with m1, the system becomes non-inertial. So what we are doing now, we're studying the motion of m2 in the non-inertial coordinate system centered on m1. Let's emphasize it. With origin in m1. R is a radius vector of m2 in this coordinate system. So simply speaking, it is a vector connecting m2 and m1, beginning at m1 and ending in m2. And for that radius vector, we got the differential equation of motion, which followed from the first, second, and third Newtonian laws and uh, the Newtonian law of gravitation, we got R double dot, where dot means differentiation with respect to time, if you remember. Dot is differentiation with respect to time. R double dot was equal to minus mu R divided by R cubed, where R in the denominator is a scalar. So R is simply the absolute value of R, and mu is the universal gravitational parameter, G, times, which is a constant in the Newtonian gravitational law, times m1 plus m2. Okay, so now we need to study this equation. It is already much simpler equation than separate equations for radius vectors of m1 and m2 in the inertial system, which we got originally. So let us do further simplifications. Let us do the following. Multiply this equation by r itself, the left-hand side, and the right-hand side. So we get r times r double dot equals to obviously minus mu. Multiply, I mean making a vector, a cross product. We will also do a dot product later on, but for the moment we need a cross product. Minus mu over r cubed, obviously r vector product with itself. But this is what? R cross product with itself. Zero. You are absolutely right. This is 0. So the right hand side is 0, which is already an interesting thing. So, okay. In coordinates, so originally we would see R is some coordinate vector, right? So x, y, z, for example, right? So what is r double dot in this case? R times r double dot is the cross product of those vectors x, y, z, and if r is x, y, z, then r double dot is x double dot, y double dot, z by z double dot. The derivative of a vector over time is just a vector whose components are derivatives. Same for second derivatives and so on. So let's see what we have here. We have again a three-dimensional vector. So for the first component, you remember what we would get? We would get y z double dot minus z y double dot. For the second one, it is not xz but other way around, zx double dot minus now xz double dot. And for the last one, it is of course xy double dot minus yx double dot. In each column, there must be a permutation of y, z, x, z, x, y, z, x, y, y, z, x. Everything is correct. And this is equal to 0. So it must be 0, 0, and 0. Okay? Now what does it mean? Let's consider, for example, the first equation. What is yz double dot minus zy double dot? It's not obvious, but I claim that this is nothing else but the derivative over time of y z dot minus zy dot. We'll check it. Or writing same in the dot notation, it would be y z dot minus zy dot all dot. Dot means the dot means differentiation with respect to time. Why is that? Okay, let's really expand the right hand side and see. So what do we get if we expand it? Okay, expand. So it is y dot z dot plus differentiating the product. First differentiating the first term, so we get y dot, the second one is unchanged, that dot, plus y z double dot, minus differentiating this z dot y dot, minus, because there is a minus in front, z y double dot. Two terms cancel each other, and we really get y z double dot minus z y double dot as was in the left hand side. So simply what we did, we guessed that yz double dot minus zy double dot is a derivative of similar expression actually, which involves only first derivatives. And obviously same applies to zx and xy. So what in fact we get is that this is a derivative over time of the vector, yes, y z dot minus z y dot. Here we have zx dot minus x z dot. Here we have x y dot minus yx dot. But what is this vector?
I guess the dot product of dot times f.
Well, it is xyz cross product with x dot, y dot, z dot. Because you see, we had a cross product of x, y, z with the vector of double derivatives. It was this containing double derivatives. So when we replace double derivatives with single derivatives, we get obviously a cross product of x, y, z with x dot, y dot, z dot, and therefore it is a cross product of r times r dot. So this is actually r times r dot dot, and that is 0, if you remember. So r times r dot derivative is 0, a 0 vector. So if a derivative of a certain vector over time, which is by itself variable, obviously both r and r dot change over time, but the derivative of its cross product is 0. What does it mean if the derivative is 0?
It's constant.
Yes, it necessarily means that the vector is constant. So r times r dot is a constant vector which we denote by h. And this is a constant vector. Now let's see what it means geometrically. What is geometrically a vector of r and r dot? So yes, there is a certain vector. You remember m1 is the origin now. There is a certain radius vector r connecting m1 and m2. And there is a certain So that's a position vector of M2. R is a position vector of M2. And then there is a certain vector R dot, which is actually the velocity vector of M2. And this is a velocity vector. What we can say geometrically is that obviously I can do a parallel translation of R dot so that the beginnings of both vectors are the same. This is also R dot, right? Then the vectors of R and R dot define a certain plane, and the vector of R times R dot is orthogonal to that plane. You remember the definition of a cross product? Geometrically, it is a vector orthogonal to both multiples. And this is a constant. Which means that the plane, because vector H is orthogonal to the plane in which R and R dot lie. And this vector is constant. Therefore, both R dot and R lie in that constant plane. So, once again, H is orthogonal to the plane of R and R dot, which means, and obviously it is a constant, and therefore R and R dot always lie in a constant plane. From which it immediately follows, a very fundamental fact for us and a very useful one, that the motion of M2 relative to R1, relative to M1, is planar, 2D. So it's not like if, for example, we do XYZ centered in origin, which is M2, and that, we have a trajectory like this of M1. No, it's not this. M1 always moves in a fixed plane. Sorry, M2. The center is other way around. The center is M1 and the motion of M2, obviously. No, it is not like that. The motion of M2 occurs in some fixed constant plane relative to M1. So a more appropriate picture would be the following. So we have, yes, our original spatial three-dimensional coordinate system x, y, z. The origin is M1. And now there is a certain fixed plane and there is some kind of trajectory of M2 in this fixed plane in a three-dimensional space. So what does it mean? It means that from now on, we can greatly simplify our task and consider only a two-dimensional problem, well, for the moment. So for the moment, we can reduce our analysis to a two-dimensional problem of M2 moving in a fixed plane. And the vector h, as we know, is the vector orthogonal to that plane. Probably one more clarification here. If r and r dot, the vectors of r and r dot, always lie in a constant plane, it means that, in particular, because the velocity vector itself is lying in that plane, then there is no velocity component which moves our body outside of this plane, and therefore the motion always occurs in the same plane.
Excuse me, can
Yes?
you tell me what is constant plane?
Okay, what is a constant plane? A constant plane is a plane which is constant over time. You see that, in general, we have two vectors, okay, r and r dot. But obviously, the vector r depends on time, because the body is moving. R dot is a function of time as well. At any time t, we can consider the plane, a particular plane, which is made by vectors r and r dot. Well, just, we have already studied the geometry of the plane. We know that two vectors, which are not collinear, so in the generic case, if r and r dot are not collinear, they define a plane, right? You can always make a plane out of two vectors. How? Really, just, the normal vector to this plane would be a cross product of r and r dot. But in general, if r and r dot are varying upon time, then the plane in which they lie would also be different. So, for example, you can think that at another time, that would be r, that would be r dot, and that would be a completely different plane. But in this particular case, we say, no, that's not true. The dot product of r and, the cross product of r and r dot is always constant. So it does not depend on time. So the orientation of this plane, although the magnitude of this vector may change, oh, by the way, it doesn't change either. R times r dot is a constant even in terms of not only orientation, but the magnitude. But what is important is that this instantaneous plane in which r and r dot lie at any time t doesn't depend on time. So it is the same. And that's what I mean by constant plane. So the radius vector and the velocity vector of our body M2 always lie in the same plane irrespective of time. That's what I mean by constant plane, irrespective of t. And now it is very easy to see that this is indeed the plane in which the whole trajectory of M2 occurs. Because if r and r dot always lie in the same plane, in particular, M2 itself and its velocity, this means that, well, first of all, yes, vector r always lies in the same plane, and this is sufficient. And secondly, yes, vector r dot also lies in this plane, and this means that there is no velocity component which tries to move our body out of that plane. So yes, indeed, this means that the motion occurs in the same plane. Is it clear enough?
Yes, thank you.
Okay. And now, because it is a planar motion, we can introduce two-dimensional coordinates. So let us introduce then axis in this plane, which I will denote by psi and probably eta, with the corresponding normal vectors as usual, I and j, if we want. So this two-dimensional coordinate system in our plane, it can be arbitrary, but for the moment, what I did for the psi axis, I took the intersection line between our original xy plane and the new plane. So that's the intersection line. This is just for convenience. Later on, we can change this coordinate system if we want. For convenience, xi is the intersection line, as you can see here, between the plane xy and our orbital plane. By the way, now this the plane in which the motion, two-dimensional motion of our body occurs, is called the orbital plane, where xy is some fixed plane associated with our original xyz coordinate system. So what would be xy, we can see later. For the moment, we are working in the orbital plane. So if the motion occurs in the orbital plane, so in the orbital plane, we can say that the radius vector is simply what? The normal vector of O psi, which we denoted by I times psi, plus j times eta. And we don't need a third coordinate. It is a planar one. And obviously r dot is r psi dot plus j eta dot. And we can consider, instead of x, y, z, we can therefore consider two-dimensional coordinates, psi and eta only, in this two-dimensional plane. Okay, so in particular, this means that if we consider this equation r times r dot equals to h, this means that psi eta dot minus eta psi dot equals to some constant h, where h is the absolute value of our vector h. Obviously, this vector is orthogonal, as we say, the vector h is orthogonal to our plane, or our orbital plane, so orthogonal to our psi eta plane, which is already a very good step. To simplify the things further, we will now introduce polar coordinates in our psi eta plane. So the first step which we did actually, the first step was obtaining this equation which we did last time, r double dot equal to minus mu r over r cubed. So that was our first step. Now a second step, we proved that our motion is a planar one, which is obviously much easier to analyze than the general three-dimensional motion. Now, step number 3, introduce polar coordinates. In this psi eta plane. And by the way, you obviously understand that without proving that the motion is planar, we wouldn't be able to introduce polar coordinates. In the general three-dimensional case, we would only be able to introduce spherical coordinates, right? You remember spherical coordinates. Polar coordinates are for two-dimensional coordinate systems only. So for coordinate systems really associated with a plane. Okay. Polar coordinates, so psi is r cosine phi, actor is r sine phi. So geometrically, this is our angle phi between O psi axis and the radius vector of M2. And the length of this vector is r. Right? Okay. So what can we do? We, having introduced this plane, now we need to find the equation of motion for M2 and find the equation of motion. By the way, in real astronomy, you can think that M1, which is now placed in the origin, is, for example, the Sun, and M2 is any planet, for example, Earth, Mars, Jupiter, whatever. Or let's say M1 is the Earth itself, whereas M2 is the Moon or any of our artificial satellites. Or maybe M1 is Mars, and M2 is one of the moons of the Mars or interplanetary probes orbiting Mars. Typically, we would put, although it is not necessary, but typically in real life situations in astronomy, we would put the body with bigger mass in the origin, so we would probably think that M1 is greater than M2, although for our equations it doesn't matter at all. The motion is relative, and although we say that yes, the Earth is orbiting the Sun, exactly same geometrical situation would be if we put the Earth itself into the origin and let Sun orbit Earth, which then leads to very interesting questions actually. And if the motion is a relative, which model is more correct from the physical reality point of view? And the answer is, we are studying our motion in a non-inertial coordinate system, as you know. We get rid of our inertial coordinate system when we placed our origin in one of the orbiting bodies. So from the Newtonian physics point of view, none of the coordinate systems are inertial or canonical. So then you can consider whatever coordinate systems. Actually, they are all just geometrical abstractions which help us to study the motion rather than, let's say, the physical reality. But we can ask which coordinate system is more close to the inertial one. And then yes, if, for example, M1 is significantly greater than M2, then if we consider, if we have time, we may do it, going back into the inertial system, we would see that M1 almost doesn't move in the inertial system. It does, obviously, but its orbit is very, very small in the inertial system, where the orbit of M2 in the inertial system is almost the same as the orbit of M2 in the non-inertial system, which we consider at the moment. So a coordinate system centered on the body with a mass far greater than the other one is much more close to the inertial one. And that's why we justify the Copernican uh, model of the solar system. It's not that just the sun is the global center of the universe. Of course not. The sun is not the center of any inertial coordinate system. But considering reasonable inertial coordinate systems, how to construct them is a task for astrometry, which is a division of astronomy. We could say that the coordinate system associated with the center of the sun is reasonably close to the inertial one. Whereas if we associate a coordinate system centered on, for example, some asteroid or a planet or artificial Earth satellite, then that coordinate system would be very far from inertial. So, but none of them is strictly inertial. We're studying the relative motion in this case, and yes, let's assume that, just to be comfortable with the common sense, let's say Copernican model, let's say that we put the body of a greater mass in the origin. There are, by the way, situations, for example, in binary stars, where both masses m1 and m2 are nearly equal, very much comparable, in which case neither coordinate system associated with either the first star or the second star is close to the inertial one, which is quite a typical situation as well. And still, it allows us to consider the model for the relative motion, remembering that it is relative only in a non-inertial coordinate system, and only then ask a question actually whether we can consider the system to be quasi-inertial, and if not, then how can we return to a purely inertial coordinate system. Okay, so introducing our polar coordinates, we, in order to find out what the equation of motion of M2 motion is, we have to return to the original equations. So you remember there was the original equation R double dot equals to minus mu R over R cubed. And now we consider this in 2D. Okay, so now R, because we know that the motion occurs in 2D, is psi eta. Obviously, R dot is psi dot eta dot, and R double dot is psi double dot eta double dot. We need to rewrite these equations in polar coordinates. Why would we do it in polar coordinates? It simply simplifies a lot of things tremendously, as we'll see. Again, no one would tell us in advance that using polar coordinates is a good idea. Originally, it could only be obtained by trial and error. What if we introduce polar coordinates? Okay, let's see. So, first of all, in the original coordinates psi and eta, this equation becomes psi double dot equals to minus mu psi divided by R cubed by taking projection onto the psi axis, and eta double dot is equal to minus mu eta also divided by R cubed, where R is the square root, obviously, of psi squared plus eta squared. Now, by introducing the polar coordinates, we also need to introduce the corresponding derivatives of them over time up to second order derivatives. So what we get psi dot equals to differentiating the right hand side, and remember that both r and phi are functions of time in general. So in that case, psi dot is differentiating the first multiple. It is r dot cosine phi minus r phi dot sine phi. Correct? And eta dot equals to r dot sine phi plus r phi dot cosine phi. Is it clear? Any questions about this? All fine. If all fine, let's endeavor to compute second derivatives. Okay. Psi double dot, watch me carefully, please, because it's so easy to make any mistake here. Differentiating the first r dot cosine phi term. It is r double dot cos phi is unchanged minus r dot phi dot sine phi. Correct? Now differentiating the second term. The second term contains 3 multiples. So at each time, only one of them is differentiated, the other 2 are unchanged. Therefore, we get minus r dot, differentiating the first one, others are unchanged, phi dot sine phi, minus r phi, now double dot, differentiating the midterm, sine phi, minus r phi dot, now differentiating sine phi, which would yield cos phi and phi dot as well. Okay? Which is r double dot cosine phi. These two terms are identical, so minus 2 times r dot phi dot sine phi minus r phi double dot sine phi and minus r phi dot squared cos phi. I think that's probably correct. At a double dot, differentiating this once again. You see, we have at a dot, now differentiating once again. R double dot sine phi plus r dot phi dot cosine phi. Now differentiating the third term, the second term, r phi dot cosine phi. Once again, I'm using a very easily established fact from analysis. You know that xy, for example, dot is x dot y plus xy dot, and in a similar way, xyz dot is x dot yz plus xy dot z plus xyz dot, and so on. By the way, it's very easy to derive formulas for derivatives of a product of 4, 5, and so on multiples. At each moment, only one of them is differentiated, others are unchanged. I'm absolutely sure you have seen something like this in your mathematical analysis. So r double dot sine phi plus r dot phi dot cosine phi plus r dot again phi dot cosine phi from the second term plus r phi double dot cosine phi minus, because cosine derivative would be minus sine, r phi dot sine phi phi dot. And this is equal to r double dot sine phi plus 2 times r dot phi dot cosine phi plus r phi double dot cosine phi minus r phi dot sine phi, phi dot squared sine phi. And at the same time, from these equations, substituting psi and eta in the right-hand sides, psi is r cosine phi, therefore r in the numerator and denominator would vanish. We can say that at the same time, from here, it is equal to minus mu cosine phi over r squared, and this one is equal to minus mu sine phi over r squared. Let's stop and look at what we got. So in the equations which are underlined, there is no psi and eta anymore. In these equations, there is only r and phi. In the right-hand sides also r and phi, and their derivatives with respect to time. R dot phi dot r double dot phi double dot. And you can probably think that what the hell we have done? Instead of a relatively compact original equation, so you see this is a relatively compact one. Psi double dot is minus mu psi over r cubed. Eta double dot is minus mu eta over r cubed. Okay, r is square root of psi squared plus eta squared. Now moving into r phi space, we got those tremendously long equations. So the question is whether there is any advantage of doing that. But you can see that, the terms in both equations look suspiciously similar. We have cosine phi here, sine phi here, sine cosine. Okay, sine is different. Sine cosine, cosine sine, cosine sine, which probably tells us of something. So what we'll do, let us multiply the first equation. Multiply the first equation by cosine phi, because we have r double dot cosine phi here. Multiply the second equation by sine phi and add them together. What do we get? Well, Maybe it's easy if we write it. Okay, in the first term, it would be r dot cosine squared phi, r dot sine squared phi. When we add them together, we just get r double dot. Because the first one is multiplied by cosine phi, the second one is by sine phi. So we got r double dot on there. Now, this term is multiplied by cosine phi, so we have minus 2r dot phi dot sine phi cosine phi. Here, plus 2 times r dot phi dot cosine phi sine phi. 0 when we add them. This term, minus r phi double dot sine phi cosine phi, plus r phi double dot cosine phi sine phi. So what? Zero again, right? This term, here we wouldn't get a 0 because the sign is the same, minus and minus here. Minus r phi dot cosine squared phi minus phi dot squared minus r phi dot squared sine squared phi. Cosine squared plus sine squared is 1, therefore it is just minus r phi dot squared. Here, minus mu over r squared cosine squared phi plus sine squared phi, which gives us 1. Therefore, it is equal to minus mu divided by I squared, r squared itself. R double dot minus r phi dot squared is equal to minus mu over r squared. That's what we got. Again, I would like to ask you whether it is clear.
I have one question.
Yes.
You said that phi is a function of time. How do we denote our phi?
How would we know our phi, you mean?
Yes, how can we take the derivative of a function which we don't know?
Oh, that's completely normal. We just know it is a function, and we leave this derivative. You say, yes, we have phi dot, for example, and r double dot here, but we don't have their explicit form yet. Okay, never mind. If we don't have the explicit form, then keep it unevaluated. It is just a derivative of the function phi and nothing else. So we don't know it yet, unfortunately, so you are right. We will know it. But for the moment, we just say that phi is phi of t. And by phi dot, we simply say it is the derivative of phi of t. It is an unevaluated symbol. We don't know whether it is a sine or cosine or whatever. We don't know. In a similar way, r is r of t. We simply say r dot is unevaluated derivative of r of t. And r double dot, we can say anything else, but just say, yes, it is a double derivative. It is the second derivative of r of t over t. We don't know it yet, but what we do know is that when they become known, and eventually they will become known, then they will be connected by this equation. This is called a differential equation, actually, an ordinary differential equation. And later on in your second year, you will study ordinary differential equations in much detail. For the moment, it is sufficient for us just to keep these symbols unevaluated, and in the hope that sooner or later they will become known. And when they become known, then yes, they will be connected by this type of relationship. Okay?
Sorry, I have a
Yes?
at the next line you have result minus mu over R cube,
Uh,
but
you
on
see,
the
you see. No, that's all correct. Here it is minus mu psi over r cubed, but psi is r cosine phi. So 1r is cancelled, and therefore here we have just minus mu cosine phi over r squared.
yes, but when you write R double,
Oh, here you're right. Yes, of course. Here it is squared. You're right. Yes, absolutely. Minus mu over r squared. Yes. Thank you. And so that's the first equation which we have obtained, and it is already a nice one. Now, one more thing. You remember that we had this, the first actually equation we obtained, which is r times square, sorry, r cross product r dot equals to h, or it was psi eta dot minus, already in two-dimensional coordinates, psi eta dot minus eta psi dot equals to h, where h is a constant and being the absolute value of h. If we can say that actually the h vector is h times k, where k is the normal vector orthogonal to our ing vectors. We have I, j, and k. I is for our xi axis, j is for our eta axis, and for k we do not even introduce an axis because we don't need it. We only need xi and eta. We have a two-dimensional motion here. So how would this one be converted into polar coordinates? Because we can do this one in polar coordinates as well. So looking at these expressions for psi and eta dot, it would be r cosine phi eta dot, which is r dot sine phi plus r phi dot cosine phi minus eta, which is r sine phi, and for psi dot we have here r dot cosine phi minus r phi dot sine phi, all equals to h. Now for the terms containing r and r dot, r dot cosine phi sine phi minus r dot cosine phi sine phi, so they vanish. Only for the second terms we have r squared phi dot cosine squared phi, minus minus is plus, therefore r squared phi dot sine phi. Therefore from this all together we get yet another very simple expression, r squared phi dot equals to h. Okay. And if r squared phi dot equals to h, what we can do, you see we have phi dot in the first equation. Again, we don't know what phi of t is as a function. Later on we'll see. But we do know that r squared at any time, r and phi are functions of time, but r squared phi dot equals to h. So we can express phi dot equals to h over r squared. And now substitute this into the first equation where there is a phi dot. So we get r double dot minus phi dot squared is h over r to the power 4, and therefore it would be h over r cubed equals to minus mu over r squared.
Shouldn't it be h squared?
H squared. Yes, thank you. It is h squared. H squared over r cubed. Okay, so we got this. What should we do from this point? In general, what we got, this is yet another ordinary differential equation, and now actually it is a better one than the first, because this equation only contains r of t and r double dot of t. So this is an ordinary differential equation which connects the radius vector itself and its second derivative of time. We don't know this r of t and r double dot of t yet, but as you will in 1 year know, that this ordinary differential equation can be solved. So we can really solve it and obtain the explicit function r of t, which follows from this equation. The only problem is solving this equation. First of all, it's something which we didn't study yet, and secondly, even if we did, it is a tremendously complex, well, I wouldn't say tremendously complex, but very, 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 very tedious thing to do in this original form. But what we can do, we can simplify this equation far enough so that the solution would become almost obvious. And then we obtain this solution. So I would say can be solved directly, but let us simplify it further. Yes, I must say that in these final lectures, 2 1/4 lectures on our analytical geometry and linear algebra, we are going into relatively deep matters, and we see we already touch upon ordinary differential equations, which you will only see in 1 year. But you will see now that there is nothing dramatic about this, but very tedious. So simplify it further. How can we simplify it? You see, there are divisions by r squared and r cubed. There is r in the denominator. So I guess, again, I'm making an ansatz that it would be simpler if instead of r, I introduce the inverse of r. So let u of t be another function, which is 1 over r of t. Okay. Or, obviously, other way around, r is 1 over u. Okay. In that case, r dot is minus 1 over u squared times u dot. That's quite obvious, right? R double dot, which we need to, I wouldn't say compute because we can't compute it completely, but express y u dot u double dot, and then substitute in the original equation. R double dot is what? Differentiating this further. Minus u double dot over u squared, differentiating this, plus keeping only u dot, differentiating this minus 1 over u squared, which gives us with plus 2 over u cubed times again u dot. Therefore, it is minus u double dot over u squared plus 2 times u dot squared over u cubed. Probably correct. Please watch. And therefore, having expressed r double dot, we can now say that from this equation, minus u double dot over u squared plus 2 times u dot squared over u cubed minus h squared now multiplied by u cubed equals to minus mu u squared. Multiplying both left-hand side and right-hand side by the largest denominator, which is u cubed, we get minus u times u double dot plus 2 times u dot squared minus h squared u to the power, oh my god, 6 equals to minus mu u to the power 5. Well, it doesn't look like a big simplification, but you will actually see that it does help quite a lot, interestingly enough. What can we do? So we got this, and in addition, we have our equation. We had our previous equation that r squared times phi dot equals to h. By the way, this equation has a very interesting geometric meaning, which we'll discover later on. Obviously, r squared is 1 over u squared, and therefore we have phi dot equals to h times u squared. So now let's do the following trick. Okay, we got this equation. So far it is not that much exciting, but let us consider the following. What do we need to do actually? We say we want to determine the trajectory of motion. So what is the trajectory of motion? If we have let's keep our objective in mind. What is the trajectory of motion, of M2 motion?
Some to
It can be given in a number of ways. It can be given as two functions, for example, psi of t, eta of t. So for any t, you would be able to compute psi and eta. And this, first of all, gives us coordinates as functions of time, which is a very good thing. And the same thing defines a parametric representation of the trajectory, because you can, in that case, think that t is not only time, but just a parameter, and you get a parametric representation. Or you can, in polar coordinates, you can, in a similar way, do a trajectory in the form r of t, phi of t. Or in our new strange coordinates u and phi, you can even get u of t and phi of t. And if you get u of t and phi of t, then from u you get r. And if you got r of t and phi of t, then of course you can easily get psi of t and eta of t by just taking psi equal to r cosine phi, eta equals to r sine phi. So if we solve for u of t phi of t, we get r of t phi of t, and then we get psi of t eta of t, if we solve it. For the moment, we didn't. Or we can even do the following. We can obtain functions u of phi and phi of t. And this is an interesting thing. So the function u of time, it defines only the geometry of our trajectory, but it doesn't say how the body is moving along that trajectory over time, because phi is just the polar angle. So basically you get u of phi as 1 over r as a function of phi, from which you get r of phi, and you get the trajectory as a shape. But it doesn't say how we move along this trajectory over time. But if you have phi of t, or phi of t in addition, then of course what you can do, you can say that u of t is equal to u of phi of t. U of phi is supposedly known, not yet, but it will be. Phi of t is supposedly known, not yet, but it will be. Then we get u of t. From u of t, obviously, we get r of t as 1 over u of t, from which we get psi of t as r of t cosine phi of t, and eta of t is r of t sine phi of t. So all the transformations we have done so far, they do have a reasonable meaning. And the final thing which remains to be done, we would like to get this function u of phi. And interestingly enough, it is relatively, probably it is one step away from what we are currently doing. My only request to you, please verify this equation. So whether we have done everything correctly. I believe that yes, we did. Multiplying by u cubed minus u times u double dot plus 2 times u dot squared minus h squared, unfortunately u to the power 6, equals to minus mu u to the power 5. Okay. Now suppose that we are trying to find the function u of phi. By prime, we will denote the derivatives with respect to phi, not t. So for example, u prime is du d phi. U double prime is second derivative of u with respect to phi. then let us, assuming that, again, we don't have them, but assuming that we do have u of phi, u prime, u double prime, let us express the dots, the derivatives with respect to time. U dot is du dt, which is du d phi dt. But du d phi is this yet unknown u prime. D phi dt is phi dot. And we know that phi dot is h times u squared. So we have h u squared u prime. Correct? Okay. Now, a bit more complex stuff. U double dot is du dot dt, obviously. U dot we already know it is h u squared u prime. So h is obviously factored out. H d dt of u squared u prime. The derivative over time can be replaced with the derivative over phi. So we can say it is h d phi of this u squared u prime d phi dt. D phi dt is again our phi dot. Therefore it is h phi dot. And now we only need to expand this derivative in the brackets. It is obviously 2 times u prime because we are differentiating with respect to phi, times u prime again, plus u squared u double prime. And therefore, it is, what is phi squared? Phi squared, phi dot. Phi dot, we know again, it is h times u squared. Therefore, it is h times hu squared times 2 times u prime squared plus u squared u double prime, all right? Which is factoring out one u, h squared u cubed, 2 times u prime squared plus u double prime. And that's u double dot. Now getting back to our original equation, here is our original equation. Minus u times u double dot and so on and so on. Let's keep it in mind. Minus u, I'm afraid that you would not see it when I move the screen. Minus u times u double dot plus 2 times u dot squared minus h squared u to the power 6 equals to minus mu u to the power 5. Okay. Can we make it visible? Oh yes, by the way, if I do it that way, then you can see both. All right. So let's rewrite it. So then it is minus u times u double dot, and for u double dot we obtain this. So we get minus u, and here we have u cubed as well. So minus h squared u to the power 4 times 2 times u prime squared plus u double prime plus we have 2 times u dot squared, but for u dot we have this. Therefore, 2 times, and it is squared, u to the power 4 u prime squared times h squared times h squared minus, again, h squared u to the power 6 equals to minus mu u to the power 5. We can immediately divide both left-hand side and right-hand side by u to the power 4, assuming that, u is never 0, because u being equal to 0 corresponds to r being equal to infinity. Therefore, we get minus h squared 2 times u prime squared plus u double prime plus 2 times h squared u prime squared minus h squared u squared equals to minus mu times u. 2 times h squared u prime squared with plus and minus cancel each other. Oh, so a horrible equation with degrees of u up to 6, as we got originally, appears to be a very simple one, actually. So now we have the first term and the third term cancel each other. We get minus h squared u double prime minus h squared u squared equals to minus mu u, which allows us to divide by u again, and we get minus h squared u double prime equals to, let me put it that way, minus mu plus h squared times u. Although, no, sorry, we don't need that, but although it is correct. So, okay, now dividing by minus h squared, it's probably better to keep u in the left hand side. Minus, let's put this term into the left hand side and this one into the right hand side. It will be more instructive. Minus h squared dividing by u double prime okay, like that. Minus h squared u double prime minus h squared u equals to minus mu. Let me put it that way. Now dividing by minus h squared both sides, we finally get u double prime, that is the easiest form, plus u equals to simply mu divided by h squared. And that's all. So we got a very, very, very simple equation with respect to u and phi, actually. So u double prime is a second derivative of u with respect to phi. Oh, we're in one step from solving it. Okay. What does this equation you have no doubt seen already? You have seen it. What is it? Well, suppose that there is 0 in the right-hand side. Instead of mu over h squared, you have a 0. What would it be then?
Differential equation of колебания.
Oscillations. It is the equation for harmonic oscillations, and you are absolutely right. You have seen it already many times, including your physics and even maybe school physics. So for the moment, forget about the constant term, mu over h squared for the moment. Then u double prime plus u equals to 0 is a so-called harmonic oscillator. Moreover, it is a very good harmonic oscillator with frequency equal to 1. Because we have coefficient just 1 in front of u. Then we already know the solution. For that one with 0 in the right-hand side, the general solution is, you already know, for harmonic oscillations, u of phi, not of t, is some kind of amplitude cosine phi plus phi 0, where a and phi 0 are constants. Obviously, instead of cosine, you can use sine, because cosine and sine would turn into each other depending on the choice of phi 0. Let's say cosine. A times cosine phi plus phi 0. Unfortunately, we have a slightly different equation. We have an equation with mu over h squared in the right-hand side. But it is extremely, extremely, extremely easy to modify our equation to accommodate for the right-hand side as well. Because if you now look at this original equation, which is marked with 3 exclamation marks, can you just guess the very simple solution to this equation to this one? If we substitute u equals to the right-hand side into the equation, right-hand side is a constant. It is mu over h squared. The right-hand side is a constant. So if you take u equal to that constant, then u double prime is obviously 0, because it is a constant. And u equals to mu over h squared satisfies this equation. Very simply. And this allows us to say that if you take the sum of harmonic oscillator and this constant, it will satisfy this equation as well, and it will be our solution. So then solution to is the following. It is a times cosine phi plus phi 0 plus this constant, mu over h squared. This is our u of phi. Why? Because the first term, a cosine phi plus phi 0, it satisfies the harmonic part, u double dot plus u. So when you substitute it into the left-hand side, you will get 0. And when you substitute the second term, into the left-hand side, you will get this term itself, mu over h squared. And therefore, the right-hand side is exactly what we want. For this term, a cosine phi plus phi 0, taking second derivative plus the term itself yields 0. For the second term, it yields this term itself. Therefore, applying our u times u double prime plus u to this solution, we indeed get the right-hand side. You can very easily see it by direct substitution. Okay, after all this wondering, we immediately got, well, not immediately, but we got what we want. We got our solution u of phi. Just very little remains to be done in this lecture. I would like to ask you whether everything is clear up to this point, because there were quite a lot of substitutions. So eventually we got our u of phi. Is it clear how and why it is a good thing?
I can see it.
Yes. Wonderful. And then it remains to recall that u of phi was just 1 divided by r of phi, from which it follows that our solution for r of phi is 1 divided by all this, mu over h squared plus a cosine phi plus phi 0, or multiplying by the inverse h squared over mu, the numerator and the denominator, we have h squared over mu divided by 1 plus, this is a constant, a h squared over mu, which is also a constant, cosine phi plus phi 0. Okay, if for the moment we neglect phi 0, okay, let's say phi 0 is 0. We have a constant 1 plus another constant cosine, let's say phi. Or actually, what if instead of phi plus phi 0, I simply say it is, let's say, some another angle which I denote by v. This constant will be denoted by p, and this constant will be denoted by e. So p is h squared over mu, e is a times h squared over mu, v is phi plus phi 0, and then we have r as a function of v, not phi. R of v equals to p divided by 1 plus e cosine v. What is this?
And
This is a general equation of a second order curve, a conic, in polar coordinates. So not necessarily an ellipse, but it might be. General equation of a second order curve in polar coordinates R V. In particular, if eccentricity is 0, E is eccentricity. as we have seen from our conics part of the course, E equals to 0, it is a circle. E from 0 to 1, in general, it is an ellipse. I would say in general, because there could be some degenerate cases. In particular, by the way, P is obviously non-zero. Sorry, non-negative. It is greater than or equal to 0. Regarding E, we don't know because it contains mu is positive, obviously. H squared is at least non-negative. E can be arbitrary because it contains an arbitrary constant A, absolutely arbitrary. And phi 0 is arbitrary as well. So if, for example, we have P greater than 0, as normally would be, P equal to 0 is a very degenerate case. If P is greater than 0, then E equal to 0 corresponds to a circle. Between 0 and 1, it is an ellipse. E equals to 1 corresponds to what? Eccentricity is 1.
So like parabola.
Parabola, you're absolutely right. E equals to 1 is a parabola. E being greater than 1. Hyperbola. Another question is whether it would make sense, for example, to have E negative here, E less than 0. I would say no. Why not? Because we can always, if for example, if E is less than 0, less than equal to 0, then we can do a substitution. So instead of V, we would use V plus pi. And instead of E, we would use minus E. And therefore, we would be back to the original equation with non-negative E. So the opposite. So the opposite case. You can have, because E is AH squared over mu, A is arbitrary, you can have E is negative, although it does not make much sense either, because in the original solution to the harmonic oscillator, A is an amplitude, so it is quite convenient to consider A being greater than 0 anyway. And if A is greater than 0 anyway, then E is greater than 0 also. So we don't even need to consider this. Okay. And in the original R and phi coordinates, this is simply a rotated second order curve. So it is a second order curve in RV, but V is simply phi plus phi 0. So what does it mean? It means that suppose that there is a certain angle of phi 0 here. V is phi plus phi 0. So for example, psi eta, this is phi, and therefore if it is an ellipse, then it would be, let's say, an ellipse like this with the major axis, rotated counterclock, rotated in this case clockwise at the angle of phi 0. Okay, so we have established the very fundamental fact. It is the first Kepler's law. In our case, it says that the two-body motion, the motion of a body, let's say, the relative motion of a body in the two-body problem originally Kepler was referring to planets moving relative to the sun, but we say in general the relative motion of a body in the two-body problem is first of all, is along a second order curve in a plane. It is a planar motion and our trajectory is a second order curve. As you see, we still don't know how this motion occurs in time. We only obtain the shape of the orbit. We still do not have solution for phi of t or v of t. So if we have v of t, then phi of t, then from that we would have r of t, and from that we would have psi of t, eta of t. In the next lecture, all those relationships will be established. But for the moment we are done. Thank you very much for your patience, that you managed to survive without a break, and we're continuously attentive to this complex stuff. If any questions, please ask. This is our AV, which is 5 plus 5, 0. Okay, thank you. We are done for today.
Thank you. Goodbye.
Thank you.
Thank you, goodbye.
Thanks.
Goodbye. Goodbye. Thank you.
Bye, everyone.